Thanks everybody for coming today. My name is Carol Jones. I'm chair of the IAU Working Group on Active B stars. This is actually my last term as chair, and we're hoping to have a vote this summer. So if many of you that have been coming each week, if you're interested in joining our group, please feel free to put your name forward. We've been working on increasing our membership from several other research groups as well, and that's going really well. So we expect to have elections later this summer. So watch for announcements on that. And if you are a member of the IAU already and you wish to become a member of this particular working group, you simply have to write me and I'll add you to the list that I'm now, which is growing kind of rapidly actually in the past few days, and I will send it into the secretary on your behalf. So if you'd like to join our group, we'd be more than happy to have you. This is going to be our last talk for the summer. We're going to take a little break for summer vacations in July and August, and then hopefully restart this really nice, very successful seminar series in September. So today we are privileged and delighted to have Ylva Götberg here. Ylva did her master's degree in Sweden, and then for her PhD moved to the University of Amsterdam. And that's where she first started working with massive binaries. She finished her PhD in 2019, and since then has worked at the Carnegie Observatories as a postdoc. She initially had the Alvin E. Nashman Theory Fellowship, and then was awarded the prestigious NASA Hubble Fellowship in 2020. Her PhD was completely theoretical and computational, but because she's at the Carnegie Observatories, she has much opportunity to work with observations. So she's actually starting to incorporate that in her work as well. So thanks so much for joining us today. And we are really delighted to have you, and we're really looking forward to your talk. So please go ahead whenever you're ready.
Thank you so much, Carol. That was a really nice introduction. And I really look forward to giving the talk. So let's see if I can share my screen. Can you see the screen well?
Looks fine to me.
Okay, great. Yeah, so thank you so much. Today I will give you a presentation about some recent and ongoing work that I'm doing here at Carnegie Observatories. And it's focused on interacting massive binaries, in particular stars that are stripped of their hydrogen-rich envelope through a binary interaction, either via mass transfer, such as you can see in the background of this presentation slide, or common envelope ejection. If you have any questions during the talk, please feel free to interrupt me. I will try and look for questions, but I may miss it. So if there is something, just let me know. Okay, so I wanted to start with a takeaway message because it's a pretty long talk. So in case you get a little bit defocused sometimes. So the main thing to remember will be that massive stars stripped of their hydrogen-rich envelope via binary interaction. They have been elusive for quite some time. But we are now starting to find these stars, and I will show you how, especially me and my collaborators, we have focused on the more massive parts of these stripped stars in the exploding regime. But there has been also some really good work on a slightly lower mass regime, including the BE stars by Lushan Wang specifically, and Douglas Geese. And yeah, so that I wanted to mention as well. To start off, I wanted to give you a brief outline. So I will start with a little bit of background on massive stellar evolution, go into the theoretical expectation for the stripped stars, and look a little bit closer at what the ionizing radiation that we're expecting. How we designed the survey based on these theoretical expectations, what's the results of the survey, which is actually starting to come together now. And then a little bit on what you can do with these results, which I think is really quite exciting. So let's begin with the background on the massive stellar evolution. As you all know, probably this is a very simplified picture of how stars evolve. At the top, you can see the most massive stars, and at the bottom, you can see solar type stars and how they swell up and then create compact objects. Many may argue that this is a very simple picture and even a too simple picture, because actually it is in some cases even inaccurate for massive stars, which tend to evolve slightly differently. So what do I mean with that? I mean that most massive stars are in fact in so close binary systems that interaction occur. It's forced to occur as the stars swell up and fill their Roche lobes, start to interact with their companion, changing that evolutionary picture, simplified evolutionary picture of NASA. So this diagram is from Maxwell Moe and Rosanne Di Stefano in 2017, and they synthesized a set of different observational works where people had been looking for what the fraction of binaries is for different mass of stars. So you can see on the y-axis the sort of fraction of stars that actually interact in the binary system as function of the most massive star in each system. And this is a really steeply increasing curve, and once you reach above, say, 5 solar masses, the majority of the stars actually are going to interact with the binary companion. And when you reach the massive O stars, this is just rather rule than exception, right? So what does interacting binaries really mean? I'm sure many of you are already familiar with this. This pie chart, I think, sums it up in a simplistic way. So this is the most common types of binary interaction we can see summarized here for massive O stars from the survey by Oksana and collaborators in 2012, where they inferred here that a third of all massive stars, they are going to lose their hydrogen-rich envelope through envelope stripping, either mass transfer or common envelope ejection. About 14% are subject to mass accretion. And so why that's not the same pie chart size, because they are just the 2 stars in each system, like the background of my background. This has just to do with here they selected just the O star, and usually the accretor is maybe a little lower mass. And then we have this pi, the quarter of the stars that actually thought to merge. So it's quite extreme. There is many other types of binary interaction, and some that are included in each of these. And it can be a lot of fun and a little overwhelming, right? So I have chosen to focus on this envelope stripping part. And just so that we are all on the same page, I want to show you a silly little cartoon that I made at some point, so that we all realize what's going on. Okay, so what just happened here? So we had the most massive star in the system to the left. It started to evolve first. It expand, fill its Roche lobe, and start to transfer all that hydrogen-rich material to the companion star. And the companion star, it spins up, and maybe it becomes a BE star. And then you're left with this binary system where you have this hot stripped helium core that is maybe called a stripped star or a stripped helium star or naked helium star. They have many names. And this rapidly rotating companion star. So let's see. let me just move this zoom bar. Then why is it so interesting to work with these stripped stars? They have actually, apart from being kind of cute, they have also various roles in different parts of astrophysics. First, they are thought to be the main progenitors of hydrogen-poor supernovae. If you look at this pie chart here, this particular one was created by Nathan Smith in 2011, and where he shows that a third of all core collapse supernovae are lacking hydrogen, and that really much resembles that cartoon from Selma, showing that a third of all massive stars lose their hydrogen-rich envelope. It matches pretty well. In fact, also, there has been some, starting to be at least now, some discoveries of pre-explosion images where you can see what type of star it was that exploded. And they all seem to have low ejecta mass, so suggesting that it is in fact not a very massive Wolf-Rayet star that gives rise to that hydrogen-poor supernova, but rather a small hydrogen-poor star. On top of that, stripped stars are also thought to constitute necessary steps for the creation of neutron star binaries that are so close that they reach a merger. So, because for neutron stars to be in such a close binary, you need the progenitors to interact. So here is an example, a cartoon created by Thomas Tauris in 2017, where you start off with a binary, then the most massive star evolves first, Phyllis Rushlow, create this first stripped star over here. And that's created through Rushlow overflow. Then we have this supernova. In fact, it's a hydrogen-poor supernova. It creates a neutron star. You have perhaps a phase here of X-ray binary, where the neutron star is accreting material from the companion star. Eventually, when the companion star evolves, the mass ratio is so large that you're very likely to evolve through a common envelope. And if you're lucky, what is left is a separated binary with a neutron star and strip star number 2. And that one was created now through a common envelope ejection. This may also go through a X-ray binary phase. And actually, when it's like this, I think it's a really fun system because those are also so tight that they radiate gravitational waves in the LISA band. So hopefully we can see some of those in the future when LISA is launched. And that eventually, the strip star, it explodes and you create a double neutron star that, because of the previous common envelope, they are now so close that they can merge within the Hubble time, create a black hole, or yeah, how do we know what object it is? So in fact, strip stars constitute several necessary steps, and there is lots of good reason to think that they are interesting. So let's move then to what do we expect for these strip stars? What really are they? How they look like, etc. And I wanted to do that starting with telling you a little bit about myself. So I started off mostly as a theorist, working with the stellar evolution and spectral modeling of hot stars. So I do evolutionary modeling with the MESA stellar evolution code, and also it's particularly focused on the binary interaction that is now included in MESA. And I model the atmosphere using this non-LTE radiated transfer code called CMFGen. With both of these codes available, it has been quite tempting to work with stellar populations as well. So I have written a small stellar population code that is particularly focused on stripped stars, and I will show some brief results from that as well. So let's look a little bit at how the structure and evolution looks like for the stripped star. So here I'm going to show you the case of mass transfer. This starts with just a single star in the Hertzsprung-Russell diagram, where you have effective temperature on the x-axis in the reverse direction, and luminosity on the y-axis. This 12 solar mass single star, B star, it starts off relatively blue, and it evolves redder and redder until it eventually explodes as a hydrogen-rich supernova. The picture changes if this star would have been in a binary and go through envelope stripping. So then the track changes direction completely, right? It goes instead to the high temperature regime, and then it doesn't have any hydrogen, so it explodes as a hydrogen poor supernova. Most of the time after this mass transfer phase is spent over here in the really high temperature regime, where the stripped star is burning helium to carbon and oxygen in the core. So it actually spends a lot of time as a very hot object. And in fact, if you look at the, maybe you wondered here, what's the shading? So the blue shading in the background is showing you the fraction of the emitted flux that is ionizing, taking a simple Planck curve assumption. And indeed, this star is going from emitting basically no ionizing flux at all to sending out the majority of its photons in the ionizing regime. So that can be quite interesting if you're interested in ionizing photons, and I have some previous work on ionizing flux as well, but I have chosen to focus now a little bit more on the stars themselves. So is really just the spectral energy distribution of a Planck curve, is it good enough though to represent the spectrum of a stripped star? Here is the flux on the y-axis, wavelength of on the x-axis, and it's really smooth, right? That's the best you can do with just the structure model from ESA. But if you model the atmosphere, you can do a better job. So this is what I spent much time trying to quantify. What's the ionizing emission rate from stripped stars? In this case, this initially 12 solar mass star, it became a 4 solar mass stripped star, and it emits about 80% of its flux in hydrogen ionizing regime. It's kind of sensitive here in the helium plus ionizing regime, and it's something that I'm currently working with. So that's also really fun, I think, if you're interested in that. But for the moment, let's leave the ionizing flux and go to some number prediction. So have you ever heard about a stripped star? Like that's not commonly something that we talk about. And how common should they be? This is now number predictions from simple stellar population model. Here's for a starburst. So if you have all stars formed at time 0, and then after about 10 million years, because I account for stars up to 20 solar masses, you start to create these stripped stars. And there is several hundred or so throughout the evolution of this a million solar mass cluster-ish starburst thing, until this population is too old. And so if we put this in context of some known clusters, it turns out the cluster needs to be very massive in order for you to have a sizable amount of stripped star in the system. So for example, recently Westerlund 1 was claimed to be about 10 to the 5 solar masses and maybe 10 million years old. So there could be between 5 and 20 stripped stars in that cluster. But if you would have 1,000 solar mass cluster, it's quite unlikely that you will see any of this at this moment. If you consider continuous star formation, here for 1 solar mass per year star formation, you can see that when the population reaches equilibrium, there should be several thousand of stripped stars that are with masses between 3 and 8 solar masses. So definitely in the regime of stars that explode. And so, for example, in the Milky Way, there should be several thousand of these, and in the Magellanic Cloud, several hundreds of these. So that's a quite large stellar population, in fact. So we should look in those bigger populations. It's easier to identify a larger population. So to summarize, what are we looking for? What is a stripped star? They are hot, typically between 30 and 100,000 Kelvin. Small, less than a solar radius. They span a range of luminosities between maybe 10 and a million solar luminosities, all depending on the mass. And simply from the mass transfer or mass loss sequence, they are supposed, probably, they are helium rich and hydrogen poor on the surface. So if I ask you what type of star is that, some may say, it's a Wolf-Rayet star. But others may say, no, that's a subdwarf. So none of that is technically wrong, because if we look at the mass range of helium stars, the subdwarfs, they are here in the low mass regime, and the Wolf-Rayet stars, they are there in the high mass regime. Most of the time, what I'm talking about is the thing in between here, where we have the progenitors of emerging neutron stars, strip envelope supernovae, things like that. And those, we actually don't have a name really for that spectral type. And I will show you a bit on that spectral type now in a little bit. And if you have suggestions, of course, please feel free to share with me what to call that. So now to how we decided to design this survey for the stripped stars, and what techniques we use to actually find them. This is a project that I started primarily with Maria Draut and her PhD student Bethany Ludwig at U Toronto. And there has been other people involved, and we are hopefully also getting more people involved with time. But I wanted to show you how we designed the survey and how the first results of it. So this is based on what we have been calling UV excess. So if we look here at the spectral energy distribution of 4 solar mass stripped stars, as we did previously, you can see that it is emitting most of the light here in the ionizing regime, which is not so great because we don't have any instruments in that regime, but it still looks pretty bright in the optical and ultraviolet. So maybe it's easy to see there. However, the strip star tends to have this companion star. Here I put a relatively low mass companion, but you can see if you just look in the optical, basically the light, it has the same color. So it's really hard to identify the strip star just through optical color. And you may need actually to use this ultraviolet regime where the strip star has a bluer color than this B-type companion. So how does that turn out? How can you use this? We decided to create a color magnitude diagram in the ultraviolet regime. So here you can see this Swift filter minus the regular V filter, and the Swift filter on the y-axis. And there are some single stellar tracks here for reference. Here are some models of stripped stars during the helium core burning stage that I created. And if you pair one stripped star with a main sequence star, it can end up somewhere here. So that's actually exactly this example that I showed you here to the right. And you can see that even though it became a little redder because of the main sequence companion, this system still occurs blue dwarfs of the 0-age main sequence. It's marked here in gray. And that is a way to find candidate stars. That if we find stars that are blue dwarfs of the 0-age main sequence, you may be able to see them as stripped star systems. And so there is many combinations that you can create here. I decided to make some wild guesses, very low mass companions, maybe really blue objects. And if you reach high mass companions, unfortunately, you will not be able to see them as they overlap with the main sequence. So exploring the possibilities here, I would say that we found there is expected to be 3 main spectral morphologies in the optical at least, and they are based on the different light contributions of the 2 stars in the system. So we have the one where the strip star is really dominating, it's so much brighter than its companion, or where the reverse is true, where the companion is much brighter than the strip star, or where you have a contribution from both of the stars. And you can see, for example, if we look closer here in the optical regime, In the case where the strip star is dominating, there is a bunch of helium-2 lines, and maybe these nitrogen-5 features, which really signifies high temperature. Whilst in the case where the companion dominates, it really looks like a B star. And in between, you can see a combination of those two. So we decided to call these out of better, we didn't come up with better names. So the one where the strip star is dominating, call it isolated, it looks isolated, and where the companion star dominates, because this is always going to be a B-type star in our case, it's a B-type. And then we have the composite in the middle. And so that's the prediction of what we expect them to look like. And if we look again in this color magnitude diagram, they cover different regions. So not so weirdly, the isolated class is expected to be the bluest, and then you have these composites in between, and then a little sliver here of the B type. So looking at what type of systems we're sensitive to with this technique. So here is a diagram showing you the mass of the strip star on the x-axis and the mass of the companion star on the y-axis. Each of the dots is a spectral model combination. You can see that I had some problems here when the stars become cooler, simply because CMF-Gen is it's not created for making stars cooler than 10,000 Kelvin. Here are the different spectral morphologies. So the isolated ones are primarily here with higher mass strip stars, lower mass main sequence companions. And then when there is roughly equal mass of the two stars, we expect there to be this composite morphology. And then for a little higher mass companions, it's really easy for them to just simply dominate everything. This is really related to the optical flux, of course, and so we found that the isolated class occurs when the strip star dominates more than 80% of the flux in the optical, and on the other hand, if the B-type companion is dominating by more than 80%, it would look like a B-type basically, and just to show you where the technique is sensitive. So here is what is going to be overlapping with the main sequence when you use this UV excess technique that I described to you. So really, you cut out most of those B-type systems where you don't see the strip star. So this UV excess technique, it's sensitive to primarily the lower mass companion stars, less than 6 solar masses, so not going to have any O-star companions here. And in the isolated class, primarily the main sequence companion, it must be of low mass, and the strip star is a little bit higher mass. So this is maybe primarily common envelope systems because of that large initial mass ratio. And the B-type that we can see with the UV excess technique is confined mainly to lower mass strip stars. So maybe it will be primarily for more massive subdwarfs that we can detect in that regime. And it's so it is definitely most sensitive to non-conservative mass transfer and common envelope ejection using this UV excess technique. And I should mention also that most strip star systems are expected to actually overlap with the main sequence and not be detectable with the UV excess technique. Instead, we are sensitive to maybe 5 to 20% or so. So that makes it really, really interesting to find how do you find the ones that are overlapping with the main sequence. And I think that Lucian Wang and Doug Gies have worked well with a very interesting technique on the cross-correlating UV spectroscopy of BE stars and actually finding a sizable sample of faint hot companions, and so that is a promising technique and really highlighting how important it is to get UV spectroscopy of stars. So now let's look a little bit at the actual observational results and and how these strip stars may look like. So to actually use the technique I described, we needed some data. So we started with using these Swift UVOT maps of the Magellanic clouds. And so these are covering most of the large and small Magellanic clouds, and this the magnitude limit is about 18 magnitudes, so you get the brightest stars, which is good for the strip stars actually, because they are quite bright in the UV. And the spatial resolution is a little bit unfortunate sometimes, because there is quite a few crowded regions in the Magellanic clouds. So that's something that especially Bethany, a PhD student in London and Toronto, has been working with. To complement this, we used the optical maps by Zaritsky of the Magellanic clouds, and they are quite deep. So actually, this reaches quite deep in both of the Magellanic clouds. And we chose to work in the Magellanic clouds simply because we know the distance very well to them. And also they have a little extinction, so you can actually see like UV bright stars quite well. So here was the theoretical prediction, right? That we would have this region blueward of the 0H main sequence. And this is now actual data in the large and the small Magellanic clouds. Here are the 0H main sequences. And for reference, we added this darker 0H main sequence, roughly marking where the B stars start, and the lighter one where there is the O stars. These are some Wolf-Rayet stars in both of the clouds. Most of the Wolf-Rayet stars are brighter than this. And in the LMC, there is also these WN3/03 stars that were discovered by Phil Massey and Catherine Nugent. Down here, we have the spectral models for strip stars. And in fact, when we looked closer at these candidates that you can see in between these models and the 0H main sequence, we found quite a spectroscopic sample. So these are the stars that we decided to look at the optical spectra and see if we could see these different spectral morphologies. So we did that using the Magellan telescope down in Chile. So here is an image. Magellan is a 6.5 meter telescope. There is two, in fact. We used the Bade one, which is this on the left side, and it has a medium resolution spectrograph called MAGE. It covers a wide wavelength range between roughly 3,500, 3,700, and 7,000 or so. And these candidate stars have magnitudes roughly 17 to 20 V-band magnitudes. So we needed quite long exposure times to actually see the spectral features well. And after several observation runs and stacking, we could put together some decent looking spectra, typically with a signal to noise ratio between 30 and 100. I think one we have 154. And so going from the prediction, which looked like this, we actually found some really similar types of stars. And so here you can see 3 stars from that sample, from the top, middle, and bottom. And I want to highlight to you here, we can see some pure helium-2 lines that are present in the top and the middle spectrum, but are not present in the bottom spectrum. And this indicates a really high effective temperature, typically at least above 30,000 Kelvin. Over here, we can see some strong Balmer lines in the bottom spectrum, and I would also claim in the middle spectrum. And that is usually a very common in B-type stars, so one of the best ways actually to see that the companion is a B-type, I found. And so in fact, what we are looking at here on the top, we think this is one of those in the isolated regime. In the bottom, that's a B-type, and then in the middle, it's a composite. In fact, the one in the middle is an actual composite. We have seen some motion of the helium-2 lines in one direction and the helium-1 lines, I think, in the other direction. So in different components in that spectra. We have worked mostly with the isolated and the composite class simply because it's so much easier to see the stripped stars in those systems, but we're continuing to observe the stars in the sample and to be able to make sure that they are all binaries also in the p-type sample. So I will focus now on the stars in the isolated group and show you their spectra and look into their stellar properties, which actually are their stellar properties from an observational perspective. So here is a diagram showing you the optical spectra. I'm going to fill it in. On the bottom, you have a helium subdwarf, and on the top, you have some Wolf-Rayet stars. And this is now how our spectroscopic sample looks like. So you can see that indeed it matches relatively well with that subdwarf, but actually when you increase in luminosity here, which is the sequence, you can start and see features that start to be a little similar to those Wolf-Rayet stars that we maybe growing somewhat. However, it's very different from the only massive or intermediate mass stripped star previously known, so that this is a spectrum from Grow and collaborators in 2008, and it's of the quasi-Wolf-Rayet star in the system HD 45166, which is about 4 solar masses as well. You can see it's really clearly an emission line star and has narrow emission, which is not at all what we can see in these stars in the Magellanic clouds. So that is a very puzzling why there is such a difference. But I will show you later that I'm pretty convinced that we anyway found stripped stars according to their stellar properties, at least. Actually, the stripped stars that we found are more similar to these very, very early O-type stars. We can even see that nitrogen doublet here when you compare to spectra from Walburn and collaborators in 2002. So how do we find the stellar properties of these stars? So I thought the most robust way should be to create a grid of spectral models and fit to these spectral models and obtain the best fit model and find errors. So I started to create this grid of spectral models with CMF-Gen for a different surface hydrogen abundance and surface helium abundance. They are with a low surface hydrogen abundance, I put a high surface helium abundance, etc. And for a different range of effective temperature and surface gravity. And then we fit them to selected spectral lines for each star. So here you can see an example where the best fit model is this thick line, and then the small, the thin line are the acceptable models within 1 sigma. So here we chose to fit to these helium and hydrogen lines that are primarily in the blue, and I chose those in this particular case because they are unaffected by nebular contamination. But if there wouldn't have been so much nebular contamination in the later lines, it would have been completely okay to use those as well. And we calculate then the chi-square to obtain the best fit surface gravity, effective temperature, and surface hydrogen and helium abundance with their errors. So this particular star turned out to have effective temperature of about 75,000 Kelvin, high surface gravity of about a G of 5, so Dex, I think it's called, higher than the main sequence typical value of 4. And it has some hydrogen left. So the surface mass fraction of hydrogen is about 0.35, meaning that the surface mass fraction of helium is about 0.65. So there is hydrogen, but not so much hydrogen. So clearly there was a little bit left. So it's quite interesting to see that it got hydrogen poor, but not hydrogen free. And to obtain then the bolometric luminosities, we fit the models, acceptable model to the photometry that you can see here to the left, accounting for extinction. I think this is a pretty good fit, and the extinction is quite low. You can specifically see it in the UV, which I really like. And then we calculate from the bolometric luminosity and the effective temperature, the radius of the star, which is 0.8, a little bit less than solar radius. And the masses are quite uncertain. So, I mean, we can state something maybe between 2.5 and 4 or something like that. It matches best in the HR diagram with the 4 solar mass stripped star in this particular case. So we did this for all of those isolated stars, and here is a summarizing table with effective temperatures. You can see that they are typically between 50, 60 and 100,000 Kelvin. Surface gravities are typically around 5. There are some stars that appear to be hydrogen free, and others that have a little bit of hydrogen, but none of them seem to be hydrogen normal, so to say. They are all helium rich. And I would say that this effective radius or radius of the star matches, so it's roughly 1 solar radius, and the masses that we expect are roughly between 2 and 8 solar masses, something like that. So if you place them in the HR diagrams, you can see the spectroscopic sample in the large Magellanic cloud here and in the small over here. And indeed, they overlap with these evolutionary models between 2 and 8. This star 17 is an interesting one. I think it's a little bit inflated, maybe not so different from, for example, Phi Persei, which I think is a fun system too. It happens to be observable in the Magellanic Cloud because it is inflated when the luminosity is also a little bit higher. So something that I want to highlight is that given this spectra that we now have observed, if we look at the models that they made back in 2018, I mean, we expect them, they're actually quite different compared to what we expected. So I expected here quite some emission features and maybe even P Cygni, things like that. But we don't see it. And this indicates that indeed the mass loss rates are significantly lower than what was expected previously. And so when I made that model grid here in 2018, I assumed a relatively high mass loss rate, actually something that originates from an empirical Wolf-Rayet wind mass loss scheme. And instead, we need to decrease that wind mass loss rate at least by a factor of 10. And mass loss rates to match models here, you need a mass loss rates of less than 10 to the minus 8 solar masses per year. So this is no Wolf-Rayet stars, and we can expect it to be even less Wolf-Rayet if you go to even lower metallicity. So some other things to notice there were some hydrogen in some cases, suggesting that they may end up as to be supernovae. And with more hydrogen, these stars can expand further later, and that's also quite fun because then they have another interaction phase and can, for example, if they orbit compact objects, initiate X-ray phases, or even more tighter systems. So just to summarize the observations, the stripped stars that have low mass companions or compact companions, they should be possible to be detected via this UV access if you know the distance well and have lethal extinction. We identified tens of these systems in the Magellanic clouds and found that they are hot, typically between 50 and 100,000 Kelvin, compact with a log G of around 5 and helium rich, so that with surface mass fraction of helium above 0.6. And they are also probably massive enough to explode in supernovae, but we don't have any dynamical masses yet, which is the best measurement. So hopefully that's something that I can present in the near future. And to come back then to the take-home message, I think we're starting to find these more massive stripped stars in binaries. And to finish off, I wanted to show you a little bit where this can lead to, because now I focused so much on just what's the observed stellar properties, etc. So this will be just a few minutes. What the future research and what are we doing at the moment? So there's many directions you can take with with this research. So, for example, maybe you can now make more precise measurements of the ionizing radiation from stripped stars and estimate even what's the impact during of interacting binaries in the high redshift universe. You can measure the winds of hot and helium-rich stars and get a more complete luminosity range for them. And there are some constraints you can make on the formation of gravitational wave progenitors. Sometimes when the stripped stars are with compact companions, basically that's a new type of faint X-ray binary if they accrete the wind. And you can do constraints on binary evolution, for example, how conservative is mass transfer, what's the most favorable way to create a stripped star, and how often are common envelope ejections successful. You can do fun things in the interior of stars, like what's the rotation rate and angular momentum transport, what's the core structure of massive and evolved stars, maybe even what's the metallicity dependence, given that we're looking at two quite metal different populations. So this spans quite a difference in quite a range of different astrophysical research fields, from gravitational waves to interior physics of massive stars and galaxies and reionization, etc. So I think that's really fun that we can go in so many different directions. We have started to work a little bit on these projects too. So Beryl is an undergraduate at Caltech I've been working with. She's been working on the metallicity dependence of the binary interaction. Ashley is an undergraduate at UCLA that they've been working with, and she has been measuring the rotation rates of the stripped stars. Cole is postdoc in UNIMEC, and we team up to work to predict the pulsation patterns of the stripped stars. Bethany has been focusing on the X-ray binaries and the compact companions. Maria actually was the PI of an HST proposal that we got through to measure the wind mass loss from our sample stars. So me and Maria, of course, involved in all of the projects, and we have several different directions to go. I wanted to show you some ongoing things from Cole, but just to motivate why it's interesting. So here you can see my picture of a red supergiant. You can see that's this huge convective cells, and as you know, the red supergiant is a single star counterpart of stripped stars, right? In the inside there is that helium burning core. And the red supergiant structure is quite interesting, right? There's lots of fun things going on here. You have a composition gradient, you have a convective burning core that is burning helium to carbon and oxygen. There may be some differential rotation, and perhaps, who knows, some magnetic dynamo, hydrogen burning shell, lots of fun things, but it's often obscured by that convective red supergiant envelope. So it's really, really hard to explore that part of the star. However, if you strip off that convective envelope, you start to reveal now that interior. And so by just, for example, studying the surface of the stripped star, you could maybe dig into, is there a differential rotation in that part? Is the core rotating faster than the envelope, or are they the same? Or as we did with coal, to look at, can we see where is the boundary here of the convective core? So coal, the project with coal has been advancing quite a bit. So we made a large model grid of stripped stars and computed gyre models, and found that there should be an extensive instability strip covering most of the stripped stars, which is primarily in the G mode regime. And these pulsations are significantly faster than the typical beta Cepheids or slowly pulsating B stars, mainly because the star is more compact, so in the order 5 to 50 cycles per day. It traces through here today. I know this is a little complicated diagram, but these are basically the frequencies of the excited modes, and they are tracing through the hydrogen burning shell and to the convective core. So technically it should be possible to determine what's the size of that convectively helium burning core. With that, a little advertisement for future work. I would like to thank you for your attention. I'd be happy to answer any questions.
Thank you very much, Ylva. That was an excellent talk. And I, for one, really appreciated all your graphics that really helped explain things and keep us all attentive. So thank you very much. That was an excellent talk. I will turn it over to people to raise their hand or go ahead and ask questions. Just before we do that, I neglected in my announcements to thank the other members of my organizing committee, and I'd like to do so before we depart. So I'll just take just 2 minutes before everybody starts leaving. So I'd like to thank others that helped me find and invite our candidates for our seminar series. So Atsuo Okazaki, Dietrich Bada, Alex Carciofi, and Greg Wade. I really appreciate your help. And I'd also like to thank my student, Mark Suffix, who helped with all the technical issues. So let's turn it over to questions. If people wanna raise their hands, feel free, or go ahead and just unmute and ask your questions. Okay, I see Doug Guys has got his hand raised, so please go ahead, Doug.
Hi, good morning, Ylva. Thank you so much for this very interesting talk. You mentioned at the end about differential rotation and about the rotation of the stars. Could you comment at all about the rotation of these exciting discoveries that you've made? My impression from what you showed us was that they were sharp lines, so it looked like they were slow rotators. What did you find?
Yeah, thank you for the question, Doug. I think so. I decided to not yet show the results of Ashley, who has been focusing on the rotation rates, because I think that we can do much better than our current results. So at the moment we have upper limits around 100 kilometers per second. So these stars have really broad spectral lines. And that is limiting a little bit the measurements that you can do. But in some cases, there are these sharp nitrogen features that you can use. And I think that we can bring down that upper limit to maybe 40 kilometers per second or so, which should be the limit of what you can do with the spectral resolution. So I do think they are slowly rotating, but I would need to reserve a little bit of time until I can properly say more exactly if it's true or not. Yeah, so it seems like they are slowly rotating. We haven't seen any fast rotator.
Okay, thanks, Doug. Anybody else with questions? If not, I'll ask just a quick one. I was intrigued by your, just right near at the end of your presentation when you were talking about the Wolf-Rayet stars and the wind mass loss rates being about a factor of 10 less than expected from empirical models. Can you point to, do you have any idea why that's the case? Is it because they're in the Magellanic clouds, or what drives that lower mass loss rates?
Yeah, that is a very good question. And I think that there is much research that needs to be done to answer it well. I know that in particular, Andreas Sander has started off with the quest to make a better wind mass loss models for lower mass helium stars. He focused much on the Wolf-Rayet stars earlier. But something that is different that we can think of, for example, is that Wolf-Rayet stars, many of them are so bright that they the luminosity, the radiation pressure also contributes to the wind mass loss. And these are fainter objects, less luminous, so they are further away from the Eddington limit and therefore should have a lower contribution of the radiation pressure. But I do think that there is much more research needed to be done. And yeah, it's also a good question if the strip stars in the galaxy look the same, or if they are emission line stars, and I don't know that. So it would be good to come up with a survey in the galaxy as well. It's just harder because they are in the disk with a lot of extinction, different larger uncertainty on the distance, things like that.
Okay, thank you. I see Dietrich's got his hand up, so go ahead, Dietrich.
Yeah, wonderful talk. Thank you very much. You mentioned the possibility of perhaps finding new massive X-ray binaries. What would be the gross properties of these systems, and how would they distinguish themselves from those that we know already?
Thank you. Very nice question. I have done some predictive, like some theoretical work on what they probably would look like. You in the audience, you probably know much more about neutron stars and compact objects than what I do, but I made a simple assumption for just assuming wind accretion from the stripped star. So we have this stripped star now with a compact companion. And if they are very tight, in a very tight orbit, even with this lower wind mass loss rate, you can have some accretion of the wind material onto the stripped star with some simple Bondi-Hoyle-Littleton accretion. And so the X-ray luminosity is expected to be lower, maybe 10 to 35, 36 ergs per second or something like that, or even less. Depending on what's the distance between the two stars. And I guess it would also be interesting to better understand what this helium-rich material accreting onto the neutron star, how that affects the X-ray binary. So I don't know, but we have some good candidates, especially actually in this sample, that probably orbit a compact companion. Whether it's a white dwarf neutron star or black hole, we still need to do more radial velocity monitoring to understand. But it does appear, especially, so star number 3 is unfortunately not here, but that one is an orbit of 3 hours, something like that, and you actually don't fit a star like a regular star in that, so should be a companion, a compact companion. So hopefully in the future we can look a little bit more how they may differ. Yeah,
sounds exciting. Thank you.
Okay, well, thank you again. That was an excellent talk and a wonderful way to end our before our summer break. So thanks again, Ylva. We really appreciate it. Feel free for all of you to send our suggestions to any one of the organizing committee. We'd also be really happy to have other people join our organizing committee or stand for membership in our working group. So let any one of the five of us know. That would be wonderful. So have a good summer break. And thanks again for such an excellent talk to end our year of seminars. So thanks, everyone. Take care.